There we go. Okay, so we've been learning derivatives. We learned the shortcut for the derivatives. So today is about the derivatives of exponential functions and logarithms. So we will first start off with the derivative of the exponential function e to the x. And when I tell you that calculus couldn't be any easier, well, guess what? The derivative of e to the x is still e to the x. So the derivative of e to the x is still e to the x. But now, next to it is a different type of derivative. You have x to the e, which is way different than e to the x. This is x to the power of e. So when you take the derivative of x to the e, you're going to get e times x to the e minus 1, because all this uses is the power rule. So just note the difference between these two derivatives. This is e to the x, that's x to the e. Okay, so let's try it out below. Okay, so we want the derivative of f of x, so we're going to say f prime of x. And first up is, what is the derivative of 5e to the x going to be?
5e to the x.
That's it, 5e to the x. Minus, what's the derivative of 3x to the fourth?
3x to the negative 4.
4x to the negative 4.
Yeah.
Oh my goodness, kids, they're scaring me. Remember, that's a positive 4. So that
Negative.
4 comes down
Oh, I'm sorry, 3.
as a 3.
3.
So that 4 multiplies the 3, giving me
12.
12, and it's going to be x to the what?
Third.
There we go. Don't scare me when your test is on Tuesday. My
What?
goodness.
And y'all don't want a free grade.
Plus, what's the derivative of 9x?
9.
9. And what's the derivative of 16?
0.
0. There we go. There it is. There's our derivative. Any questions on that? All right. Ooh, that was rough. It's Thursday. All
Just
right.
getting started.
I'll zoom out for that one. Okay. Now we have 2. F of x equals negative 7x to the e plus 2e to the x plus e squared. So we want the derivative, and now this is going to use that x to the e formula above on the paper. So what is the derivative of x to the e?
Ex to the e minus 1.
That's it right there.
Come on.
Plus, what is the derivative of 2e to the x?
2e to the x.
2e to the x. And then what do you think the derivative of e squared is?
2e.
Tricky. So
E.
So e to the x is e to the x, but e squared, and when I say tricky, is a constant. So what's the derivative of any constant?
0.
0. So the derivative of e squared is just 0 because it's a number. Do you see any variables on e squared? And when I say variables, I mean x, y, z, or anything
No.
like that? No. So therefore, it's a constant. Here, I'll just write that in. That is a constant. Okay. All right, there you go. There's your derivative. Not bad. And then, again, number 3. 9e to the x plus 2x squared. What's my derivative going to be?
It's going to be
4x.
9ex to the e minus 1.
Careful. You're confusing
9e.
yourself.
Is it 9e to the x plus 4x?
4x.
That's it. Remember the difference between e to the x and x to the e. Follow the formula and you will be just fine.
How many x's in e?
Okay. Again, 3x to the e minus 2e to the x. What's my derivative?
3ex to the e power minus 1.
Minus.
That one's just going to be minus 2ex.
That's it.
Professor, are you recording this class?
I am. This one's recorded.
Okay.
So again, all we have done is followed those formulas above, right?
Yes.
That's it. Just make the note, just note the difference between e to the x and x to the e. If you're wondering why the derivative of e to the x is e to the x, well, it involves the limits and the difference quotient. So we could explore that later if you wanted. Okay. Next is the derivative of the natural log function. You guys remember the natural log, right?
Yes.
So the derivative of the natural log of x is 1 over x. That's it. The derivative of the natural log of x is 1 over x. Okay. But when we do log derivatives, we are going to come across some of these log functions that we have to algebraically manipulate before we can take the derivative. And if you guys remember how to algebraically manipulate logarithms, there's 3 main properties, which I wrote here for you guys. So the first property is the product to sum. This is product to sum, meaning if you have the natural log of x times y, you can expand it to the natural log of x plus the natural log of y. The next one is the quotient to difference. If you have a quotient inside your log, if you have natural log of x over y, you can make it into the natural log of x minus the natural log of y. And the last one is the power rule for logs, not to be confused with the power rule for derivatives. What this power rule does, it takes this power and brings it to the front, giving us n times the natural log of x. Now, do not make the mistake of confusing this for the power rule for derivatives. It is not the same. These are the 3 main algebraic properties rules for logs on how to rewrite them so we can take the derivative. I'll say doesn't equal power rule for derivatives. Don't get that confused. Okay. So with all these properties, let's go ahead and try out these log derivatives. And remember, we can only take the derivative of a natural log if it's in the form of natural log of x. If you see anything else there, we have to rewrite it before we take the derivative. So, number 1, you have f of x equals the natural log of x squared. So we can't take the derivative until we rewrite this. What can I do with that power of 2?
Put it in
In
front.
front of the log.
Put it in the front. You make it 2 times the natural log of x. And again, we have not taken the derivative. We have rewritten it by power rule. Now we are ready for the derivative, f prime of x, and you'll get 2 times, and what is the derivative of the natural log of x?
1 over x.
1 over x. And our answer is 2 over x. That's it. Any questions on that? All right. Now, once again, we have the f of x equals the natural log of 4 over x cubed. We can't take the derivative in this form. So we are going to rewrite this using that second property above, the quotient to difference. So what's another way to rewrite this natural log?
ln 4 minus ln x to the third.
Good. But we still have to rewrite it one more time. This log is good. This log, what do we have to do with that exponent?
Put the 3 in front.
Put the 3 in front. We are now ready for the derivative. We haven't done any calculus yet. This is straight algebra, which means we are ready for the derivative and f prime of x. And what do you think the derivative of the natural log of 4 is?
0.
0. Good, it's a constant. So you'd get 0 minus 3. And again, what's the derivative of the natural log of x?
1 over x.
1 over x. So our derivative is just negative 3 over x. All right. Using all those log properties that you learned last semester, right? Or whenever you took 1324. Okay. So number 3, no rewriting on this one. Thank goodness. Everything's where it needs to be. So we're just going to start with the plain old derivative, and you're going to get 6 times, and again, the derivative of the natural log of x. What do I get?
X.
1 over x minus what?
3x.
3x
Squared.
Yeah, 3x.
Good. And the derivative of 2 is
0.
0. So you get 6 over x minus 3x squared. Done and done. All right. Perfect. 4. No rewriting to be had again. Marvelous. We're just going to take the derivative straight up. So f prime of x, and what's my derivative?
1 over x.
1 over x plus what?
2ex.
2 e to the x minus what?
6x.
6x.
6.
That's it, 6x. Boom. Not bad. And those are the derivatives of natural logs. Everybody good with this page?
Yes.
All right. You guys remember those properties from above?
I have a question.
Go ahead.
The only one that kind of confused me was number 2.
Okay.
I don't know. I got kind of lost. Do you mind just running through it one more time?
Yeah. So number 2. So we can't take the derivative in this form, right? So what
Correct.
we have to do is expand it by log properties, which means we're going to use this property above, the quotient to difference. So the natural log of 4 over x cubed becomes the natural log of 4 minus the natural log of x cubed by the quotient to difference property. Good with that?
Okay.
And now we have this as expanded by quotient to difference, but we still can't take the derivative yet because of this guy. So
Okay.
now we use the power rule for logs, and we take this 3 and move it to the front, which is right here. Which means now this statement is ready. We are ready to take the derivative of that statement because everything's in its proper form. And since the natural log of 4 is a number, it means it's just a constant, and the derivative of any constant is 0, right?
Mhm.
And then 3 times the natural log of x, well, that 3 hangs outside, and the derivative of the natural log is 1 over x.
So then it's -3 over x.
Mm-hmm.
Okay.
Good.
Sounds good. Yep.
All right. Cool. All right. So now we have the derivative formula for e to the x, x to the e, and the natural log of x. So, and we have those log properties to help us rewrite logs if we need to. Okay. All right. Now, the next two are about finding the equation of the tangent line. Oh, just like that last terrible problem, but this is going to be a lot faster because we know the shortcut now. So, example 3, find the equation of the tangent line to the graph of f at the indicated value of x. All right, so if we're going to find the equation of the tangent line, we need 2 ingredients. We need a slope and we need a point. Well, it just so happens that if we find the derivative, we find the slope of the tangent line. So I'll write that information below. So from 9.4, we did learn that the derivative f prime of x is the same as the slope of the tangent line at a certain x value. At an x value. Okay, which means using that information, all we have to do is find the derivative. So what is the derivative of 2 natural log x?
2.
2 over,
Oh, 2 over x.
right? Because it's 2 times 1 over x or
Yeah.
2 over x. And now, to find the actual slope, what x value are they giving us to plug in?
1.
1. So we're going to say m tangent at x equals 1 is going to be f prime of 1 equal to 2 over 1, which gives me 2. And there's our slope. But again, we're trying to find the equation of the tangent line, and to find the equation of any line, you need a slope and you need a point. So we have found the slope. The next thing we need to do is find the point. Here I should label this as find slope or just slope.
So is 2 over x the same thing as just 2?
When you plug in 1, it will be.
When you
But
plug
for
in
now,
got you.
yeah, the derivative is going to stay at 2 over x. And if you want to find the slope, it's just going to depend on the x value they give us, right? And the x value they give us up here is 1.
Okay.
Okay. Now, the next thing we need to do is find the point when x equals 1. Well, to find a point, you plug in an x value, and it should output a y value. So to get our point, we're going to take this value of 1 and plug it into the original function. So we're going to say f of 1 equal to 2 times the natural log of 1. And does anybody know what the natural log of 1 is?
0 because it's a constant, isn't it?
Well, that would be the derivative, but lucky guess.
Yeah, seriously.
No, see, here I didn't ask for any derivative. The only derivative I asked for is right there. Right there, the calculus was done a long time ago.
Okay.
Isn't it 1 something?
But based on your lucky guess, the natural log of 1 is always 0.
And that's only for 1.
That's only for 1, the
me
natural
write
log
that.
of 1.
Okay.
Plug it in your calculator if you want. Type in the natural log of 1 and see what it gives you. And this means we are going to get 0, which means our point is at 1, 0. Oops. Which means we have our two ingredients, which means we can now move on to the equation of the tangent line. I'll just say tangent line. And I'll use this formula we've seen before. Y minus y1 equals m times x minus x1. Remember that this is called the point slope formula. And the reason it's called that is it's telling you what ingredients it needs. It's saying, hey, in order for this equation to work, I need a point and a slope. And we have both. So,
Question.
yes.
Sorry, would they ever, like on problems, give us to find, or they would give us y equals, let's say 2, versus right now we have x equals 1, or do they always give us the x point?
They'll always give you the x point, but if they gave you the y point, well, you should know how to solve for that.
It's the same thing, yeah, right?
Well, it'd be a little more complicated with the logs, but yeah, if you
Okay.
plug in y, you'll get an x. But you won't get anything like that. Not in this class. All right. So my point is x1, y1. So we're just going to plug all this information into this point slope formula. So I'll get y minus 0 equal to my slope of 2 times x minus my x1 value of 1. And then y minus 0 is y. Distribute the 2. And there's our tangent line, y'all. That's it. Any questions on that?
So what we just found, that's the,
That is the tangent line that shares the point 1, 0 with the function 2 natural log x. It shares that point and it takes off. So if you want a visual, why not? We have the time. Good old Desmos to the rescue. Let me just organize this and this and this. All right. So let me go back. Graphing calculator. And this is just a visual of what you found. I have y equals 2 natural log. Where are you? Right there. Y equals 2 natural log x. And then nope, x. And then my equation over here is y equals 2x minus 2. And there it is, guys. If I zoom in, there's the point they share, 1, 0, and takes off. So that's what you have just found. Yeah. There you go. So that's all we found. We used that point and we found the slope of that point. And if you have that point and that slope, you can find that tangent line. So let's do it again below for the next function, e to the x plus 1. Okay. So to start with, we're going to find the slope. And remember, the slope of the tangent line is equal to the derivative. So the first thing we're going to do is find the derivative of e to the x plus 1. So what's my derivative going to be?
Let me go back on my notes. I'll tell you right now. It's going to be
1 over x.
EX.
E to the x. The derivative of e to the x is e to the x, right? And of course, the derivative of 1 is
0.
0. There we go. And now, we'll say at x equals 0, m tangent is going to be f prime of 0 equal to e to the 0th. And what is anything to the 0th power?
0. 1.
1. There's our slope. So anything, no matter what, to the 0th power is 1. Okay, so we have our slope. Now let's find our point. Find our point when x equals 0. And once again, to find your point, you're going to take the x value and plug it into the original function. So you'll have f of 0 equals e to the 0 plus 1. And e to the 0 is what?
it's 1.
1 plus 1, and we get
2.
2. So the point is going to be 0, 2. And now we have our two ingredients.
2.
We have our slope. We have our point. So let's go ahead and find the equation of the tangent line. And now we use that point slope formula. Y minus y1 equals m times x minus x1. Here's my point, x1, y1, and plug in everything we know. Y minus 2 equal to my slope of 1 times x minus 0. And you get y minus 2 equal to 1x. Add the 2 over, and y equals x plus 2. And there's your tangent line. And that would look something like this. Here's e to the x plus 1. And then here is the point 0, 2. And it's x plus 2. So you would look something like this. There you go. All right. Any questions on that page? That seemed a lot easier going the faster way, right? Everybody good with this one?
Yeah.
Yeah. All right. Let's move on. Last page. All right. One more derivative formula. So now this is the derivative of any other exponential function. So if you are given f of x equals a to the x, then the derivative of a to the x is going to be a to the x times the natural log of whatever that base is. So a to the x times the natural log of a. So that is the formula or derivative formula for any exponential function a to the x. So if we try it below on 2 to the x minus 3x, if I say g prime of x, and following that formula, what would be the derivative of 2 to the x?
2 to the x times ln 2.
There you go. Minus, what's the derivative of 3 to the x?
3 to the x times ln times 3.
There you go. So natural log of 3, not natural log times 3. Because remember, that 3 is inside the natural log. So 3 to the x times the natural log of 3. And that's it. That's ugly. Can't do anything else with it. All right. Which means this brings us to our final question. Application. The estimated salvage value S in dollars of a company airplane after T years is given by S of T equals 300,000 times 0.9 to the T. What is the rate of depreciation in dollars per year after 1 year, 5 years, 10 years? So what we're going to do is take the derivative of this function because it's asking for a keyword here. What is the rate? Meaning, what is the rate of change of good? What is the rate of change of depreciation? What is the slope of depreciation? And we know that that also means the derivative. Because remember, the derivative is all about slope. So let's go ahead and take the derivative of this function using that new formula above. So let me zoom in. And when we take this derivative, we only look at this part of the function. So I'm going to say S prime of t equal to 300,000 times, and now use that new derivative formula. What am I going to get?
0.9 t times 0.9.
There you go. 0.9t times the natural log of 0.9. There's the derivative. And now all we have to do is plug in 1, 5, and 10. So S prime of 1, S prime of 5, and S prime of 10. And good old Desmos is going to help us out. Oops, that way. All right, close that, and then 300,000. And I'm going to do parentheses and parentheses again, 0.9, close parentheses. And for anybody using the calculator, instead of t, you're going to type x. So we're going to raise this to the x, move over 1, times the natural log of 0.9. Close that, and close that. Nope, that's too many. I think I got it. Yes.
Would it also work on our graphing calculator if we were just to plug in for the t, 1 and then 5 and then 10 to see every single one of them individually?
Yeah, but make sure to have it as x though. Don't put t.
No, but that's what I was saying. Like if we were just to plug in, with not to put the t, I mean the x, but put just like 1.
Just put 1, 5. Yeah, if you put them in separately, that's fine. What I'm doing is I'm putting in that function itself, which means now I can do what you're saying. I can plug in 1, I can plug in 5, and I can plug in 10. And there's my 3 answers already. So I get negative 28,447.34, and then negative 18,664.299, so 30, and then negative 11021.08. All right. And yes, you can type them in one by one by one if you want. Here I just use that table because it's so much faster. I type in the function and I just do 1, 5, and 10, and bam, there's my answers. So our airplane that used to be $300,000 says after the first year, it has depreciated by $28,000. And then by 5 years, it'll depreciate more by $18,000. And then by 10 years, it'll depreciate more by $11,000, which kind of makes sense. It's just like you buying a new car, right? Right when you drive it off the lot, it already lost what, half its value, maybe? There we go.
Can you show us how you got that chart again on Desmos?
For sure. So whenever you type these functions in, so let's start over. I'm going to say 300,000 and then parentheses 0.9 raised to the x, move over, times the natural log of 0.9, close that, close that. So once you have typed in the function, you've typed in all the function, the next thing you're going to do is hit that gear icon above. Let me make sure I have all my parentheses. There we go. So you see that little gear icon above?
Yeah.
So you click that and you're going to see that table button.
I have a question.
Go ahead.
And I'm sorry for interrupting you. Just because I want to understand it more, when you said like how it relates to like the 300,000, like how it relates to like a car, you know, how like once you drive it off the lot. Can you explain it? And like how it was saying like after 1 year, 2 years, like the negative, what does that mean?
So the whole point of the problem was that we were finding the rate of depreciation. So this airplane, it says that after the first year of usage, it's going to lose its value by $28,000.
Oh, okay.
So that's just like any type of vehicle you buy, right? So once you have your vehicle for longer, if you bought your vehicle for $25,000, are you going to be able to sell it back for $25,000 10 years later?
Yeah, no.
No, right?
So that's what it means. Like 5 years, then it would lose it 18,000 instead.
Exactly. So I guess like in the beginning years, you lose the most. And then after that, 5 years, it's only going to decrease by 18,000. And then by 10 years, it's going to decrease by 11,000. So the longer you have it, of course, the more it's going to decrease. What was that?
Did you hit the gears button and then what?
Oh yeah. So you hit the gear button, and right when after you hit that gear button, you'll see a table button. And all you do is click that table button and it makes the chart. That's it. So I can show it again. Let's say I did just y equals x. And again, click that gear button. And you'll see that little table down below. You see like the 2 pieces of paper in the table?
Yeah, I'm not seeing that. Do you have a T in yours? Yours is an X.
I did an X. So whenever you type these into the calculator or the computer, always use X. If you use T, it's going to want to know what the random value for T is. So never use t, always use x.
Okay, now it popped up. Yeah, I
There you,
changed that to out.
there you go, yeah. Because if you put t, it's going to ask for a slider, and we don't want that. So always, always use x no matter what. And did you get the table?
Yes, sir. Appreciate
All
that.
right, cool. All right. And then on that table, you can enter any value you want for x, and it's going to give you the immediate output for y. All right. So again, our airplane every year, first year, 5 years, 10 years, the rate of depreciation is going to keep going down. So there you go. And that finishes these notes. Any questions?
So, and I'm so sorry if I'm still on the topic.
No, no.
I guess I'm still just trying to get used to it because you know how you're saying it, comparing it to a car. The longer you have it, you know, the more value you lose.
Mhm.
So, how come in 10 years it's kind of smaller than it was like in the first year?
It just depends on, I mean, that's a good question. And there could be a lot of factors involved in that, right?
Right.
So, I mean, it also depends on the function we're given. So maybe
Yeah,
this function
definitely.
starting to curve around to where your loss is just getting less and less, you know?
I think what
Okay.
she's trying to understand is, like you said, the first year it loses a 28,000,
Mm-hmm.
and then it's gonna, by 5 years it's gonna lose 18,000 more on top of the 28, and on the 10 it's gonna lose the 11,000 on top of those other two,
Mm-hmm.
right?
Yeah.
Oh,
So
Okay.
just after every year, you are losing money on your airplane or your vehicle, right? So it's
oh,
just
okay.
constantly decreasing no matter what. So why the different amount? Well, it's just how the function is panned out. Whoever made this salvage value function is saying that, okay, after the first year, you're going to lose a lot. After that, you're not going to lose as much, but your depreciation is still going down. Because eventually, after T amount of years, your airplane will be worth $0.
Right. That's why I was looking at it
Yeah.
like why it didn't make sense to me how like if like for 10 years I would lose less than how I would than the first year.
Yeah.
Is it basically supposed to mean like, you know, it's the first year it's 28,000 I lose on top, in 5 years I lose on top of that 18,000 more,
Mm-hmm.
right?
Mm-hmm.
Okay, I wasn't thinking of it like that. I was looking at it as like, okay, so in 5 years I'm losing 18,000. So how come I'm losing less than I would in the first year? You know what I mean? I
Yeah.
wasn't thinking,
It's kind of like you've lost so much value already. Then like, why should we take more value off? You know?
that's true. That's
It's like
true.
it's just decreasing, and you know that your value is decreasing. Because
Yeah.
now, let's say you've kept your car for 15 years, you take it to the dealer, and they're like, "Well, we'll give you 300 for it."
Right.
Yeah. So it's just a depreciation model. That's all it is, and it's based
I don't
and
give a
all
fuck.
it is. It's based off of that function.
Yeah. Thank you for the explanation.
Yeah. No. Yeah. It's good to understand what it is. So whatever comparisons we can make it to. We can't compare it to houses because apparently houses, their value increases over time. Like depending where your area is at, right? Let's see. Let's see if we can look at a graph of this function real fast. Maybe, unless we don't know the restraints of it. There you go. Yep, it's a natural log exponential. Oh, goodness. Oh, yeah. Since we're looking at years. Yeah. So since this is a natural log function, or an not a natural log, sorry, an exponential one, you see that as the years go by, this is all the money we're losing. So after, actually, if we went and found our values, because let me scroll down. since we're in the negatives already, which isn't good. All right, so look at that. So even after 25 years, you would lose about $2,000 extra on top of your plane. So as the years go on, this is the value of your plane constantly decreasing. So again, the decreased values are all based on whoever created this function. We just want to know at what rate, how much value are we going to lose? And I guess if you were to sell your plane, what would be the best year to sell it in to at least get some of your money back? And that's it. All right. Come on, computer. There we go. Okay, well, that finishes 10.2. So if you have questions, stick around. We have about 20 minutes left. Let me know. Other than that, we are done.